Welcome to Brain Vision.
In this question, we have a stack of blocks on a frictionless table, and the string attached to the stack of blocks passes over a pulley, frictionless massless pulley, to a third mass that's going to pull the stack, and we want to find the mass of that third block such that blocks A and B will slide together, because there is friction between blocks A and B. So traditionally, we would want to start with a free body diagram for each of the three blocks. So we're going to have gravitational force on B down, normal force on B up, and then it's going to be the frictional force between A and B that makes block B accelerate. And now if we wanted to draw a free body diagram for block A, its weight will be downward. It will be feeling a normal force from B. I'm going to call it normal force B. There will be a normal force from the table on A that's large enough to offset the pair of normal forces down. We are then going to have a tension force to the right, and then there will be a friction force backward. Ooh, actually, I should color code that one too. Hold on, that's fun. So there's going to be a friction force backward between the surfaces of A and B. So if you were A, you would feel B trying to slide backward as you begin to accelerate from block C. And now our force diagram for block C is going to look like the weight of block C. Actually, I should make that a little bit bigger because we're going to have the weight of block C, FGC, and then there will be a tension force back upward from the string that connects it to A. And we could go through and set up Newton's second law for each of these. I'm going to show you an easier way. If we look at this system as a whole, we have the weight of C is pulling everything, and then there are no resistive forces on the system as a whole. The friction between blocks A and B becomes an internal force, as does the tension. So we can look at the fact that it's going to be the weight of C that's accelerating all three blocks together. And so we'll have the mass of C times G equals, I'm going to go ahead and leave MA and MB inside parentheses times A, and then I'm going to pull out my mass of C times A on that right side. So I just partially distributed A. And this then allows me to pull my, This then allows me to pull my two terms involving the mass of C together. So I get MC times G minus MC times A equals the mass of A times B multiplied by the acceleration of the system. And now I can factor out MC on that left side multiplied by G times A equals the sum of my other two masses times the acceleration. And almost done, folks. We now have an expression for the mass of C in terms of the other two masses and the acceleration of the system. So what we really need here we need the greatest acceleration of the system so that B moves without slipping. So we're just going to home in on, sorry, I need to rewrite that so it's a little bit neater. So that B moves without slipping. So we just need to home in on the net force on B equals the mass of B times its acceleration. And it's going to be the frictional force on B from A that accelerates B. Well, let's look vertically. The normal force on, oops, let me put the right subscript. So the normal force of B will be equal to the gravitational force on B because there are no other vertical forces. And then our frictional force between B and A will be equal to mu S times the normal force on B, which will be mu S times mb times g. So we can now substitute over here mu S times mb times g equals the mass of B times A. And look at that. We get a value for our acceleration equal to just simply mu S times g because the mass of B canceled out of this calculation. Oh, come on, give me the red so I can cancel. All right. Well, cool. So we'll go ahead and substitute here. 0.750 from mu times 9.8 gives me an acceleration of 7.35 meters per second squared. And now we are ready to substitute for our mass of C. So we need the total mass of A plus B, which will be 8 plus 5 kilograms times our 7.35 meter per second squared acceleration of the whole system, all divided by 9.8 minus 7.35, and we actually get a pretty substantial 39 kilograms is the largest mass of C that we can use and still have B not slide on A.